Hey, good afternoon, everyone. Welcome again. And our next speaker of the next mini course is Hiraku Nakajima from Kavli Institute of Physics and Mathematics of the Universe,
Yes.
Tokyo. So some of you may or may not know Nakajima will be the IMU president in a few days, starting in 2023. So if you are still young enough by 2026, maybe you got a chance to shake his hand and get a medal in next ICM. Okay. Well, anyway, the title of his talk is Coulomb branches of 3D supersymmetric gauge theories and Bow varieties. Let's welcome.
Thank you very much for very nice introduction. So, I'd like to talk about Coulomb branches and Bow varieties and also geometric Satake for affine algebras. So these are references for this series of talks. So together with Bleberman and Finkelberg, we wrote 3 papers on Coulomb branches. This is the original papers. And we wrote expository papers, one by myself and second by Bleberman and Finkelberg. And also Finkelberg wrote an article for proceedings for ICM. So this is also another expository. And in the latter half, I will talk about Bow varieties, which is closely related to Coulomb branch, and also quiver varieties, which I have studied many years. And then application of Bow varieties and Coulomb branches, I recently studied geometric Satake for affine algebras. And for type A, we established geometric Satake in this paper. And the Coulomb branch were originally studied by physics and context of quantum field theory of gauge theories. And there are vast literature in physics, but during these lectures, I will not mention any result in physics. So if you are interested in such background, then please look at this paper. This is the very first paper of myself about Coulomb branch. So, and also I'm planning to post this note to my website or conference website afterwards, so you don't need to take note. And I think I prepared too much for this presentation, so maybe at some point I will switch to whiteboard. Okay. So this is review for definition of Coulomb branch. So in the morning lecture, we learned that the convolution product gives interesting algebra. And I'd like to consider similar construction, not for functions, but for cohomology groups. I took this setting. So M is a smooth variety. I only consider all the variety over C, complex numbers. M is a smooth variety, and you have a more proper morphism to X. X could be singular. Then you consider the fiber product, Z of M cross M over X. Then H star of Z has a convolution product. So definition is very much the same as the case of functions. Technically speaking, so we must be careful about which homology theory you use, and for this we use the so-called Borel-Moore homology group, which is in this setting also the cycles. which is defined by using locally finite cycles. So anyway, so you have element C1, C2, C and C prime in here. Then you define a convolution product C by the formula P1 star. So you must be a little careful because, I mean, if you have a function, then you can put back and take multiplication, and then you integrate, like in the Ewan's definition for the Heck algebra. But for homology group, so in general, you cannot put back the cycle by a morphism. So you must use the Poincare duality. So maybe so this smoothness assumption is secretly used here. So anyway, so you can switch the homology and the cohomology in this definition. And then you can do both pull back and push forward. Anyway, so this is a little technical point, but I just want to emphasize that you can define a convolution product, very much like in the case of functions. And if you have a group acting on the space like this, and also it is the pi and x has also have a group action, then you can consider you have the G action, group action on this fiber product. So then you can consider the equivalent homology. So we will use this construction for particular G and Z. And this construction, appropriate choice of M and X and G, people consider this convolution algebra, and this construction has been used to realize various algebras. So I just write several famous examples. For example, by Joyce, the degenerate alpha Heck algebra was realized. And by Baragnolo, so Yang was realized by using Quiver varieties. And in order to, for later definition of Coulomb branch, I slightly generalize the definition. So suppose I have complex reductible group G and the parabolic subgroup P, and I have pair of representation. So maybe this is important, so I keep here. So G is reductive. And you have P, parabolic. And you have B, representation of G, finite dimensional usual representation. And then consider V prime, which is not the representation of G, but this is representation P. So this is P invariant. Then you can form M as here. So this is a vector bundle over the partial flag variety. So this is a vector bundle over partial flag variety with fiber equal to V prime. Then you have a natural morphism I to X. So if the definition is like this. So if you have element in V in here, then you just multiply G times V. Right? No, what is X? X is V. X is V. So originally, small v is an element in v prime, smaller space, but since you multiply g, so this element gv. So if g is in p, then it is still in v prime, but since we are multiplying element from G, so this is no longer staying in V prime, but it's in large V. And if for affine, degenerate affine hector algebra, V is a adjoint representation, and PP is a Borel, and V prime is nilpotent Lie subalgebra. So this is an example. Any questions so far? No, X is typically singular. But in this example, I mean, in fact, usually the image of, I don't assume this is surjective. I mean, usually the image is a smaller submolet if it's usually singular. Arbitrary. V is a representation of T. It depends on the situations. Okay, so let us turn to Coulomb branch. Coulomb branch is also defined in very much similar way as this. But Coulomb branch is a variety. And we try to construct its coordinate ring, which is commutative ring. Right? So we try to construct a commutative ring by this convolution product. And then you define affine algebraic variety as a spectrum. In other words, this commutative ring is a coordinate ring of affine algebraic variety. But in most of the cases which people have been studied, those convolution products usually give non-commutative algebra. So then, unless we do have some kind of miracle, we don't get commutative algebra. But from the morning lecture, we just learned that this miracle happens for affine Grassmannian. So the Coulomb branch, definition of Coulomb branch is based on the affine Grassmannian. By that reason. Okay, so I use this notation, G of K and G of O. K is, maybe I should also keep notation somewhere. K is a formal Laurent power series, and O is formal power series. And Ziwen already emphasized that, so the geometric Satake, using this affine Grassmannian, you have geometric Satake, which identifies certain category of power shifts with, certain category of power shifts with category of representations as monoidal category. And the tensor product in the representation theory side is clearly commutative. But on the other hand, in the affine Grassmannian side, commutativity is less clear. Nevertheless, there are some reasons why we have commutativity. But in fact, we get even more interesting. So by a slight modification of the construction, we also get non-commutative algebra. So commutative algebra has a non-commutative deformation. So on the affine Grassmannian, you have so this G is a point in puncture disk. So you can rotate the disk. So everything is equivalent under this additional C star. And if you consider the convolution product in that setting, then the algebra becomes non-commutative. So it means that, I mean, of course, representation theorists are interested in representations of non-commutative algebras. So this is the object which representation theorists are interested in. But somehow, because this is a deformation of commutative algebra, some study of commutative algebra helps to understand this non-commutative algebra. So in that sense, this is a very good situation. You have non-commutative algebra, which is tightly connected with commutative algebra. So during my lectures, I mostly concentrated on commutative side, and I briefly mentioned non-commutative deformation. But somehow people should keep in your mind that you should also study non-commutative deformation of the Coulomb branch. Okay, any questions? Okay, and now we start that formal definition. Again, G is complex reductive group. Oops. And you take M, which is symplectic representation of G. The symplectic representation means that M is a symplectic vector space, and G preserves the symplectic form. But in these lectures, I assume M is of this form, N plus N. This is assumption. N plus N star. So N is a complex representation. Usual representation. And as a cotangent space to N, it has a natural symplectic form, and it is preserved by G. So, because of this reason, I will often forget this symplectic representation M. But at several points, you will see this M plays some role. And in fact, there's a recent paper by two groups of equals, Webber and others, and also Tillman. So they generalize the definition of Coulomb branches to more general M, and with some assumption on M. And in fact, I'm recently working on such example, and in the workshop next week, I will give such example of M. And K and O are like in that, like here. And then, so we take N of K. So this is for formal Roland power series with values in N. right? So then this is the representation of G of K. And here you have the subspace N of O. Instead of formal Laurent power series, you consider formal power series. And you have G of O. And this is preserved. N of O is preserved. So this is exactly the situation which I kept in here. So G, this is analog of G. And this is analog of P. And this is analog of B. And this is analog of V prime. Right? So you can apply the construction. N of K is a formal Laurent power series with values in N. I mean, N is a vector space. You have, how to say, collections of numbers, and you replace numbers by formal power series. Okay. Then, by some reason, I did, instead of M, I denote by T. So T. So this is analog of M. And then you have projection to N of K. So this is analog of X. Right. In the right board. So here you can write down formally the definition, similar definition here. So this is a pair of DZ and SZ. So now, the element depends on this variable. This is a formal power series in Z. So I denote this variable Z here. And this S of Z. The element in here is denoted in this way. And then, formally you apply the same definition. So you multiply ZZ times S of Z. So originally, S of Z has value in N of O. That means there's no negative powers. But the G of Z contains negative powers. So if you multiply, this is formal Laurent powers. It could have negative powers. Okay? So then you apply the same definition of the convolution product. Okay, so apply. So you consider H star, and on here you have an axiom G of K. So this is formally same as the thing which you consider in the finite dimensional case. This is. But unfortunately, this formal definition doesn't make sense. But fortunately, there's a very easy trick to have rigorous mathematical definition. So this is a little bit of technical point, so this is not mine. So I consider this fiber product and action of G of K. But so you can normalize the second component. The second component I did not write G. No, I didn't write it, but this is the second component. So you can normalize the affine Grassmannian part of the second component as identity by the action. And then you still have residual geo action on the space. So we are interested in the equivalent geometry since we are considering equivalent homology. But instead of this ill-defined object, you can consider geo-equivalent homology of this space, right-hand side. So this is a little bit of technical point. So this is not so use H star of O of R. So R is the fiber product, but we normalize, as I say, wrote here, the second component to be identity. This is a definition. Yeah, you don't need to worry too much about this technical point, I hope. Because somehow the reason why this has convolution product is best explained in here, I believe. I mean, even though this is a heuristic explanation, so this has pullback and push forward. And I have a convolution product. I somehow formally replace this by this, and then you have the similar convolution diagram and having you can define the product here. And technically, this space behaves much better. And those technical reasons I will not explain anyway. So if you don't really if you are not interested in detail of the definition of the convolution, then you can just ignore these differences and I switch, even though I might say this, but you just consider it. I'm considering this space. Okay? Any question? Okay, then we have this theorem. So first is, as I said, is a technical statement. So this is well defined. So as I already learned, that the affine Grassmannian is a limit of finite dimensional projective variety, and R or T is an infinite rank. T is an infinite rank vector bundle over the affine Grassmannian. But if you truncate the formal power series formal Laurent power series by finite series, then you get finite dimensional, finite rank vector bundle. And together with this treatment for the affine Grassmannian as a limit of finite dimensional projective variety, you can define this homology group as limit of homology group for finite dimensional space. And there's little complicated point whether, so when you take this limit, the degree of the homology group must be suitably treated. So you have the pullback. You need to consider pullback for this process for the taking limit. So that's because of that reason. So this homological degree could be negative in general. Maybe did I wrote that? Maybe I didn't emphasize it. Maybe from that, maybe I think I can now erase this. For in terms of R, special, what? I don't write the definition, formal definition of the convolution product. But from this, if you use this definition, then it's the usual convolution product. There's one technical issue that, so as I said, so you must use the Poincare duality to pull back the homology class. And since this is infinite dimensional space, and if you approximate by finite dimensional space, then it becomes singular. So you must really be careful why this pullback is well defined. But that is possible. So this is too technical, so I don't want to explain. But there's some delicate issue in the definition, but fortunately you can overcome all those things. Mm-hmm. 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 Yeah, yes. So I must, so maybe a good exercise that you return back to the finite dimensional situation, and you clearly have a convolution product in this M cross M. Maybe I just erase, unfortunately. So this is H star of P of, so analog of this, how to say, M was P cross P, and so this is a pair, G and V, but so you have, how to say, M cross M, and second component, subvariety. Maybe I just didn't write by R, same notation. This is G of V, G1 of V1, of V2, such that G2 is identity. Then exercise is try to define a convolution product in terms of this smaller space. This is possible. Once you solve this exercise, then somehow you see that how at least part of the definition which why we use these spaces. So anyway, so maybe. Yeah, so we don't, as I said, we need to approximate those varieties by finite dimensional varieties, but this seems to be too infinite dimensional to approximate. Yeah, that is the technical part which I don't think I can explain in these lectures. I mean, this is really about the definition, precise definition of Coulomb branch, and I think in order to understand it, you just need to read our paper. Otherwise, I mean, it's technical, but somehow, if you really want to understand the definition rigorously, then I think the only source is the original paper. Using omega k, we don't, using topological model, we don't try. Maybe Telemann's approach might be good, yeah. Yeah, maybe you wrote a good expository paper, so why don't why we use a different source for offering glass mining? Remark which maybe I mentioned afterwards, but grading. Integer grading, not necessary. And you have a convolution product. And the unit is the fundamental class over the fiber order of affine glass mining. So this is diagonal. In this description, diagonal, fundamental class of diagonal is the unit. And if you translate it into here, then you see this, why this is naturally the unit. Okay, then another interesting thing is, so equivalent homology, whatever it is a module of the equivalent cohomology of a point. So here, this equivalent, we are considering equivalent homology with respect to G of O, but this is the same as equivalent homology of G. And those equivalent homology by general cells, H star of G of O R is a module over. And this is a polynomial ring, which is well known that this is polynomial ring. I will go back to, I will give various examples of this afterwards. This is a polynomial ring. And this multiplication convolution product is linear in the first variable. So F times C1 convolution product with C2 is equal to F of C1. And later we will see that the convolution product is commutative. As I emphasized, commutativity is very much related to the geometric Satake correspondence. We take exactly the same situation, so we expect this to be commutative. So afterwards, we see that convolution product is linear also with respect to the second variable. But this is somehow you should consider this is a miracle. And in fact, it is no longer true if you consider the quantization. So as I said, quantization of the Coulomb branch is very important, and once you consider the quantization, it's not linear in the second variable. Okay. I think I prepare the definition roughly, but I think it is based on the convolution diagram of Markowitz Vilonen for geometric Satake. So I think it is better to postpone after the events. Even will explain it tomorrow. So anyway, one technical point is that you must be careful how this pullback is defined. And you also need to check associativity. This is the usual diagram chasing argument. And as I wrote here, the grading is in integers, not necessarily non-negative integers. So we have this algebra. And then, as I said, we have a quantization. So we have distraction, loop rotation. On O and K. Power sheet. So this is multiplication on Z. And it acts on everything which so far used. So in particular, this variety R. And also the group itself, you have no action on the group, which you consider the equivalent homology. Then you consider the space is the same, but you consider the larger group acting on the space. Then you have the convolution product, and it is algebra over the equivalent cohomology of this extra system. Usually this is the polynomial ring in one variable, and this variable is usually denoted by h bar. So this is we take the physicist notation. H bar is a Planck constant, and if you make h bar to be 0, it means a classical limit, and you recover the commutative algebra. Right? So this is a very easy modification of the definition, and it gives non-commutative deformation of commutative algebra. Maybe I didn't say that. So this, this commutativity is not as emphasized. The commutativity of geometric Satake is known, but it's not trivial property. So you need some effort to prove that statement. And I only give, there are two known proofs for the commutativity. And I only give one proof, which is computational, so by some reduction to the torus case. And torus case, I explicitly defined this algebra, commutative algebra. So this is this is not the satisfactory proof, but it works. And there's a better proof by Nergan. Maybe I don't know how to pronounce. So his proof is given in the appendix of our third paper. So I hope Jimen explained the proof of commutativity by using the so-called Beilinson-Drinfeld-Grassmannian. So we have similar proof, similar in spirit, I mean, by Roneman. So I don't explain this second proof at all. So anyway, once you get the commutative algebra, then you define the Coulomb branch as a spectrum of commutative ring. So this is a priori affine scheme, unless you know some properties of this commutative ring. But in fact, we also know that this ring has various nice properties. So we have a lot of knowledge on the affine Grassmannian. So we have Schubert varieties, spherical Schubert varieties, and that gives some cross-sub variety in the affine Grassmannian. And you consider pullback to this space R. And by using such kind of knowledge, you can analyze this homology group. And from that, for example, you can show that this is finitely generated. You can also show that the Coulomb branch is always normal variety as algebra variety. This is one of the very nice property of the Coulomb branch. And the proof of the normality is not so difficult. I mean, I think maybe at some point I will mention how we prove it, but it's not so difficult. I mean, then you must go to derive the geometric Satake. So I think you maybe it's not a question to me. He will. And once you have the non-commutative deformation of commutative algebra, then you can define Poisson bracket by this formula. So you have function C1, C2 on MC, then you lift to non-commutative deformation and take a commutator. Since you put h bar equals 0, it becomes commutative. So commutator is 0 at h bar equals 0. So you can divide by h bar and then specialize afterwards. Then it is independent of choice of lift, and right-hand side is well defined. You have Poisson bracket. So maybe I didn't say that properly. It is also known. So theorem which we proved in general, this Poisson bracket is induced from a symplectic the regular locus Coulomb branch. So there is a notion of Poisson variety. So that means, maybe better to consider the smooth case. You have a notion of Poisson manifold. So it's different from symplectic manifold. So Poisson manifold could be the two. How to say this? You cannot define in terms of forms, but you consider the bivector. So this bivector could be degenerate for Poisson manifold. But this symplectic this Poisson bracket is not the one which coming from Poisson bracket on the smooth. So if you restrict this bivector to at least you can restrict to regular locus. Then it comes from the actual symplectic form. It's non-degenerate along the regular locus. Okay, and in fact, is even more better. The first part is just the comment which I just mentioned. So this commutative algebra has very nice properties. And you have integrable system equipped with MC. I think this is a very interesting feature of the Coulomb branch. So as I emphasize that the algebra is not defined is not linear in the second variable for the quantization, but still you have the algebra homomorphism for equivalent homology of point to equivalent homology of the space. This is algebra homomorphism. So this is basically, so if you have a scalar here, then you multiply the scalar to the unit. The unit, how to say, so you don't need to worry about the commutativity. So this is, unit is unit, so this is algebra homomorphism. So if you have you can specialize this to be h bar equals 0 to return back to commutative situation and take a spectrum, then you have the morphism in the opposite direction. In fact, this is, you can show that this is injective. So you have a commutative, this is a commutative subalgebra. This is a commutative. As I said, this is a polynomial. This is a commutative subalgebra. Yeah, maybe before that, I should write down this one first. So you specialize h bar equals 0. Then you still have the algebra homomorphism. And as I said, this is commutative. So commutativity becomes trivial. But if you return back this definition of Poisson bracket, so you see that if you take function f1, f2 from here, then you send it here, and take Poisson bracket. So this is equal to 0. Right? So you first lift here, but still you can lift to just here, trivially in the h bar direction. Then, because this is a commutative, the commutator is 0. So right hand side 0. So this is Poisson commuting subalgebra. Poisson commutative subalgebra. So what is the integrable system? I'm not sure there's abstract definition of the integrable systems. To me, the study of integrable system is a difficult subject. There are lots of examples, and I never understand integrable systems systematically. But anyway, so you have the Coulomb branch, taking spectrum. Spec of its 0 point. 0 over. So this is the Coulomb branch. And this is, as I said, this is a polynomial ring. And it takes, if you take its spectrum, it is just a vector space. L is, in fact, rank of G. And the morphism go to in the opposite direction. This. So what this says is if you take function on here, so F1, F2 is a function on this vector space. And if you pull back to here, then they are Poisson commuting. The integrable system usually require, I mean, as I said, I don't know the abstract definition of integral system, but people usually require that, I did not this, pi, and people usually require that by the, I think this is due to, based on the Liouville's theorem, if you have compact symplectic manifold, then the fiber, and if you have Poisson commuting function, and maybe I also need to say that other things. And we show the dimension of MC is equal to 2 times L. So this vector space is half-dimensional. And also, we also show that generic fiber of pi is, so in the compact setting, I think by the theorem of Liouville, the fiber should be torus. But here, because we are studying algebraic geometric setting, so we don't have torus. So instead, we get algebraic torus. In fact, we get a check. So dual torus of the maximal torus of G. G. Complex relative when T is maximal torus. And this is dual. So in that sense, this map has a properties which is natural affine algebro-geometric counterpart of the integrable system, which appears in the result of Liouville. So anyways, we will show these two. And we say that this is a canonical integrable system attached to, which is attached to in branch. And this integrable system will play important role afterwards. Okay, I'd like to make a break here. So shall we have 20 minutes as in the previous? Okay. That might be good.
So it seems it's very close to the cotangent bundle of T-cat.
Tangent bundle of T-cat.
Which one? The Coulomb branch.
Yeah, very close, yes.
So does it contain the open part? Does it contain a copy of cotangent bundle of T-check? Only a part of it?
I mean, you must take the wire group quotient, but thanks. It's birational to cotangent bundle. modular.
But does it contain really a copy, a whole copy of continuum bundle?
That is not known.
Oh.
Okay, let me continue. So, so far, I explained abstract definition of a Coulomb branch. Now I will give some example. So first, let me start with the easiest example. Oops. I see. So the group is C star, and the representation is just zero representation. This is the most basic example. Then, because I just erased. So if the representation is zero, then so this additional power series with values in n just vanish. So you just get the affine Grassmannian as a variety. So then affine Grassmannian C star, what we just learned, this is just integers by g of n. And so we are considering the equivalent of homology of this space. But I mean, of course, this is discrete points. So the action is trivial. So you have the equivalent homology of a point at each point for the integers. So this is a total description of the equivalent homology group. But let me write. R is direct sum of n for each star of the C star point. Times g of n. And I denote the fundamental class of g of n as Rn. And I denote, so this is again polynomial ring in one variable, but this is different from the C star which appears in the loop rotation. This C star is this group G. So we should not use H bar. So I instead use variable W. So this is W. So you have this algebra for each n. You have a variable Rn, and then you have polynomial ring in one variable. So then, so this is a module structure, and you need to understand multiplication. And it is very easy to guess that what is the multiplication of Rm and Rn. I mean, I don't give the convolution diagram which define the convolution product on this. I postpone it to tomorrow. So I cannot compute it. But so Jim mentioned that this is coming, I mean, for the geometric satake, you use the compact Lie group, based loops to consider the group multiplication to realize convolution product. So maybe you could believe that this, because there's no fiber part in this example, you could define the convolution product also using this group multiplication here. Then it is clear that this is coming from Zn. Rn corresponds to Zn. So you have Z to the power m and Z to the power n. Then this the result should be something correspond to bit of to the power Rm plus n. So this should be equal to Rm plus n. And you can, and this is very natural formula, and I hope you believe that this is correct. And in fact, you can show that this is correct formally using this definition of convolution diagram. This is easy part. And then I said that this multiplication is linear in this equivalent homology for the first variable. So Fw of Rm times Rn is f of w of Rm plus n. And I said that in the second variable, it's a priori not linear, so you must be a little careful. So you must use the part of convolution diagram. And I think it is better to compute it in the case of the quantization. So if you compute a commutator in quantization, then I really need to use the definition of convolution product using the diagram. So that I postpone to explain tomorrow. But the formula is, I think, this. This seems to be most natural commutator. This is n times h bar times Rn. So in particular, if you make h bar is equal to 0, then it becomes 0. So it means that this multiplication is also linear with respect to the second variable. So in total, if you believe this formula, then you get h star of g of O bar is double. And so because of this, R0 is a unit. And you have two generators, R plus 1 and R minus 1. And of course you have this, R1 times R1 is equal, R0 is equal to 1. So this R minus 1 is just 1 over R plus 1. Right? So this is the commutative ring. So if you take a spectrum, so you take the variety whose space of function is this ring, and this is equals C star. So W is a coordinate for the first part, and R plus 1 is a coordinate for the second component. So this is the very first example of the Coulomb branch. Okay. And you can also study a little bit more. And so because of this commutation relation, so you try to understand the meaning of Rn in terms of W. So then you see that this commutation relation is something familiar one. So if you consider the difference operator, so if you shift the variable W to be W plus NH bar, so if you define Rn as a difference operator given by this formula, then the commutator, Rn commutator of Rn W is equal to NH bar times Rn. This formula. Right? So it means that this quantized Coulomb branch, maybe I forget to introduce the notation for the quantized Coulomb branch. H bar, this is quantization of Coulomb branch. And in this example, this is equal to, maybe because I shift by H bar, so this I call H difference operator. A ring of H difference operator on C. C is C of W. Right? And you can also change the role of W and R plus 1. So you consider R1 to be fundamental variable, and you look for the meaning of the variable W, which gives this commutation formula. Then there is the family one. W is differential operator, natural differential operator on C star, given by this. Then it satisfies this formula. So you have two natural viewpoints for this quantization. So this is, as I said, first one is difference operator, and the second one is differential operator, like that. But in view of the integrable system, somehow we want to consider, for example, polynomial in W's. This is a subalgebra in the quantization, commutative subalgebra in quantization. So in that sense, it is more natural to view W as a fundamental variable. So once you consider W to be fundamental variable, then you regard Rn to be the difference operator. But maybe at some different consideration, maybe another viewpoint might be. But so far, I don't know. And you can generalize to the case of torus. And as I said, as Jim explained, the affine Grassmann is co-weight lattice. And then so we want to think this as a space of functions on some space. Then somehow you must use this tautological identity. So this is the definition of the dual torus. So you change the domain and the codomain, and then you replace the torus by its dual torus. So this is the space the Rn naturally lives. And maybe I didn't explain the case of equivalent homology. So you need to use the following fact. Equivalent homology of point. So this is naturally regarded as the polynomial function on the real algebra of T, of which I denote by German T. I think this is, for example, I mean, I don't explain any definition of the equivalent homology group, equivalent homology and equivalent cohomology group. But maybe if you are familiar with equivalent case theory, then you know that the equivalent case theory of a point is a representation ring. So this is somehow a representation. So you consider the character, it gives a function, while group invariant on the function, while invariant function on the torus. And for the equivalent cohomology, then you replace the group by the real algebra. So you should get functions on the real algebra. This is one part. I mean, of course, there are lots of other natural explanation. But equivalent homology is a function on the real algebra. So you take a spectrum. So this and T is on eject system. So if you combine this, then in this case, Coulomb branch is equals T check. Right? So this is a Coulomb, more intrinsic description of Coulomb branch for this example. So this is a cotangent bundled. Right? Usually cotangent bundle is denoted by T star, but we have too many T's, so I just write plain English. So the real algebra of T check is the dual of T by this definition. And the original T is dual to the real algebra of T check. Because of that, this is cotangent bundle, not the tangent bundle. Okay? And you see that the symplectic form, Poisson bracket is induced from natural symplectic form. So this is a part of computational relation. Any question? Okay, then let us go to second example, which is a little bit more interesting. For example, 2. So G is still sister, and N is a natural representation. Then we must use the space T and R are non-trivial. So T is T of K, O, N of O. We have A, right? We have and affine Grassmann, since we know that for the G equals C star, affine Grassmannian is just integers. So somehow, basically you need to understand the T in here instead of the original T. I in this way. No? So this part. You have this R in here. So R is, maybe I didn't give the formal definition of R. So R is a subvariate in here, and maybe this is important, so maybe better to explain. So T, we consider T cross N of K T, which was D1 of G, 1 of G, G of G, G1G, S1G equal to G2G, G. Then I said that R is a variety in here such that G2G is identity. Maybe this is in the affine Grassmann. Right? So then you don't have G2B, so this is identity. Then from this formula, S2G of G, maybe in red. So S2 is determined from G1, S1. So you can also ignore S2. So we have R is G1G pair, G1G, S1G in T, but not for T, because originally G2, S2G was in T, so S2 of G must be formal power series, not the formal Laurent power series. So this condition, so you define it in this way. So you must ensure that this should have no pole in G. So this means G1 times S1G is in N of O. So a priori, maybe varieties. So return back to, yeah, so this is the general definition. So if you have element in T, and if you multiply those two entries, then it is in N of K, it could have poles in general, because S doesn't have a pole, but G could have pole, so multiplication could have. So if you impose this condition, then this is not a whole T. So this is a closed subvariety, because this is a closed condition. Okay, this is general. This is general. But if you try to see in this particular example what it really means, so take G to the N in the affine Grassmannian system and consider fibers in R and T. maybe so recall that this the T is a vector bundle of on the affine class money, and R is a subvariety, so you can still consider the projecting the affine class money, and fibers is inverse image of this morphism. So then for T, so this is maybe better to consider here. So G of Z is Z to the power N. So this is for T. The fiber is Z to the power N of G of Z. But for R, so that the multiplication must be also in polynomial. So this is G to the N C of D intersect with C of D. Right? So you have this extra condition. So this is exactly this condition means in this particular example. Right? So this is the description of the space. So in summary, what we got. So we have, in summary, so this is a picture of P and R. So we have a bunch of points parameterized by integers. And for here, on here you have some vector space, infinite dimensional vector space. So this is G to the power N of C of D. So this is T. And R is almost the same. You have infinite dimensional vector space. But instead of this, you replace smaller space. Right? This is a picture of T and R. And you need this is vector space. So this is, if you take this connected component, so the fundamental class times the equivalent of homology of point is a corresponding homology class. So you need to understand what is the multiplication. But here somehow, so there is some trick to compute it, which I described as a proposition. So you have, so this is a general result. So you have inclusion of R by T, and you have zero section, which I denote by G, to G. So this is zero section. So we consider the projection. So this is a vector bundle over the affine class money. You can consider zero section. Then proposition. So you consider I of star times pullback by Z. So this is a map from this is a general result for arbitrary G and N. This is an algebra homomorphism. So you push forward by this closed embedding and then pull back by. So this is vector, because this is vector bundle, so you can define the pullback. Although we are working on the homology group. And then you can check it. This is algebra homomorphism. So we apply this result to the case of this example. And so so we are considering that the case G is C star and the representation is one-dimensional natural representation. And this is the example which I first computed. So this gives C cross C star. So you can use the computation there, compute the convolution product in here. So then, what is the definition? I define Rn is coming from the previous example. Rn is a fundamental class of the affine class Manian, or the point z to the power n. Then Rn prime I define this as a fundamental class of a fiber R over d to the power n. So this fiber, as I said, this is d to the power n over C of B intersect with C of D. Right? Then you push forward and pull back. So then you just try to understand what is the relation with Rn. So basically, in order to compute that, so Rn was the fundamental class of this, but this is vector bundle, so it is the fundamental class of the fiber for T. So this is fundamental class. Instead of R. So then both are infinite dimensional, so it's a little bit tricky to consider. But the point is both are infinite dimensional space, but so this is always subspace, but the quotient is finite dimensional space, right? If what is I must be a little careful which is which. So if n is positive, I think if n is non-negative, then this condition, this condition is automatically false, right? This condition win. So there's no difference for R and T, right? So if n is positive, but if n is negative, then these two vector spaces are different, right? So you have, if n is negative, so this, it means that you have start with negative powers of z. So here you could have starting polynomial power series starting from g of n. But here, it must be contained in C of z. So that means, so here you have g of n, a of n plus 1 of g of n plus 1. And somewhere you have maybe a of 0 times g of 0 plus a of 1 of g of 1 here. But in order to sit in here, you must have those coefficients up to a minus 1. Those must be 0. Right? So this is a finite dimensional condition. The quotient is finite dimensional vector space. In fact, I think this is minus n, dimension minus n. So starting from a minus 1, right? And you need to consider the C star. C star is not coming from the loop rotation. This is just multiplication on the whole vector space. So each has weight 1. So then you see that Rn prime is equal to double minus n times. I hope it is clear. So this is written in here. So now then we try to compute what is R1 prime multiplied with R prime minus 1. Now it becomes easy. And also, because of this, as I said, this is algebra homomorphism, and this is commutative. And somehow you also, from this, it is clear that this is embedding. So this is also commutative. Commutativity in this case it can be proved by reduction to the first example. So this is equal to R1. So R1 prime is equal to R1, and this is W times R minus 1. This is equal to W. Right? So now the ring is different. So it's star of E of O R. In this example, it's E of W and R prime 1, prime minus 1. But you have a relation W equal minus 1. Then it means that you don't need the W. You can remove a W from this. So this is a polynomial ring in 2 variables. Therefore, spectrum is equal to C2. So this is the computation of the Coulomb branch. And I need to consider the integrable system. I mean, the quantization is, maybe I forgot to mention that. In this first example, so the integrable system is just taking this double component. So it is too easy, so I don't explain that, but somehow this is easy. The integrable system. The integrable system is defined by what? So it is coming from equivalent cohomological point, which is C of W. So this is the C, but the natural coordinate is W. So it means maybe more fancy standard notation. I replace this by X and this by Y. Then integrable system goes in the opposite. So the pullback from the base of integrable system is this W, which is X times Y. So it means that integrable system is just given by XY goes to X times Y. Okay. This is pi. And fiber. So in this particular example, you can determine all the fibers. Fine. So if W is not 0, then it is C star. Right? XY is equal to W. But if W is not 0, then this is just C star. And if W is equal to 0, then fiber is XY is equal to 0. So this is union of two axes. Right? So you have C2 and maybe I write in this way. So this is C star. If you move W, so this is non-zero W, and if you make W to be 0, then C star is going to union of two axes. This is the integral. Okay, I think. Maybe the next example is easy, and I finished it by this example. So slightly generalized. So instead of one-dimensional natural representation, you take n direct sum of n copies of one-dimensional representation. And physicists use this funny notation, one circle n and squared n. And this large n corresponds. This notation will be clear from the lecture tomorrow. So anyway, so you consider n copies, direct sum of n copies of the weight one representation. Then you do the same computation. And in this case, instead of this formula, the only difference is because, you have large n copies. Basically, you take the large n copies of this example and take direct sum. So the quotient is now replaced by large n times n dimensional instead. Then, maybe there's a typo there. So large n times n should be minus of n. Okay? Right? There's a typo here. Minus is forgotten. So anyway, so you just multiply large n. Then, instead of xy is equal to w, I just erase xy is equal to w. Instead, we get w to the power large n, right? We have this variety. So, there is a conflict of notations. But this is, I think this is okay. N 8-1. So then MOC is x, y, w, cut out y, x, y, n. So this is the Coulomb. And this has a singularity at the origin. So this is a famous simple singularity. Type an minus 1. So the origin xy is equal to 0, 0, 0 is singularity. It's a singular point. In this case, there's only one point, one singular point. So for n equal 2, if n is equal to 2, this is type A1 singularity. So that is also singularity for nilpotent conformance, which we saw in the morning lecture. So it looks very similar. I mean, I cannot draw the higher dimensional picture. This is 0, 0, 0. So this is also C2 divided by cyclic group of B over N over NZ. So for N equal 2, this is plus minus 1, so you quotient by C2 by plus minus, but in general this. Okay, I stop here today. Thank you for attention. Quantization is the proposition which I explained. So this proposition remains to be true for quantization. So you know the quantization for the first example, then you can compute quantization also in this. Somehow not the whole how to say. So you multiply something to the difference operator because, as I said, R prime 1 is R1, but R prime minus 1 is double times R plus minus 1. R minus 1, right? Maybe better right. R plus minus. So this is true for, also true quantization. So R minus 1 is the difference operator in minus direction. But you need to multiply by double. So R minus 1 is not in the quantization, but R prime minus 1 is in the quantization. So if you, what it is? I'm not sure, so I'm not expert in Daha, but if you consider the cyclotomic Daha, then you see this kind of. So cyclotomic Daha is a subalgebra in the original Daha, rational Daha maybe. And you see this kind of relation. And in fact, this is the, how to say, the particular example. So this is very close to cyclotomic Daha. But the, how to say, the symmetric group part it becomes trivial. So the first what is cyclotomic Daha is a deformation of G of n, G to the power n, group ring of this. So this is a deformation. And in this example, so we just, because, so this is one dimensional, we take n, small n to be one dimensional case. So you don't see, you only see this part. So maybe because of that, you might not recognize as this example for Daha, but actually it is. So this you can generalize this example by replacing C star by GL, small n, maybe I mentioned. Probably I don't have time to explain this result with Codera. So this is maybe better. So then, I think the first commutative part is symmetric, n symmetric power of this type n singularity. And so this is due to BFN. And the quantization, this is due to Codera and myself. So this is a spherical part of cyclotomic Daha. If you are not familiar with cyclotomic Daha, this is just some deformation of this. We have this result. Any further question? Yes. Well, so for example, if n is weight 2, then we still get by the same computation. What it is. What is the point? Maybe I just erased in here. Let me see. So weight 2, for example. Then for T and R, we need to compare C of I put the dot here. This is T, this is for R. But this is actually coming from the representation, right? So this is coming from the this, how to say? We consider this kind of multiplication, right? So then actually here you use the representation. So if this is weight 2, this must be replaced. If weight 2, this is 2 times n, right? This is the only replacement. Then for this, the codimension, only the codimension. I mean, for quantization, it is slightly different, but at least for commutative part, only in this particular case, it is slightly more complicated, I think. So you must consider the quotient space, and you must consider I don't remember by heart, but my vague memory is, in this case, we also get the type A1 singularity. In particular, so you could get the same space from a different choice of group and representation. So we have, starting from group and representation, we construct some variety, but this is very far away from injective. Any further question?
Zero copy doesn't change.
No, it doesn't change. If you add trivial representation, then it doesn't change.
So, by your GON example, why do you choose?
This is my favorite example. So if you consider this is corresponding to quiver. So this is, so I consider the cotangent bundle of this one, right? I start with the cotangent bundle this in the beginning. Maybe at some point I should explain the Higgs branch. So starting from n, we consider. Then you have the much easier way to construct a variety from this. So namely, just to take a symplectic reduction. So if you have a symplectic vector space, you have the notion of a moment map. So this is inverse 0 divided by G in the categorical, this is categorical quotient. I mean, if G is a general linear group, you can, in this particular example, you can also categorical quotient. So I add the dual part. So this is the dual. So then I usually denote this by B1 and B2, and this is A and B. So this moment map is commutator of B1, B2 plus AB. I mean, under the identification of G star and G as by pairing in a product of given by trace. And then this in fact, in this particular example, so this is slightly point. Anyway, but somehow this, I know that I have been studying this example for how many years? Maybe 40 years. So this example too is so familiar to me. But anyway, this is partial compactification. Of framed modular space. Of vector rank n, rank large n, vector bundles over B2, modification seeds, line infinity. And framing means that you have the trivialization of the restriction to line infinity. And the second Chern class is equal to. So somehow, maybe tomorrow I will, at least I will try to mention some relation between this construction and the Coulomb branches. So you get this different space. And if n, large n is equal to 2, so this is exceptional case, and let me n equal 2, n equal 1, which is, I think n equal 1. N equal 1 case, maybe this is slightly confusing, but so you have, if you put the stability condition in here, change categorical quotient by GIT quotient, you get framed modular space of torsion free sheaves instead. That also I studied. And if n equal 1, then 0 is just a C2 as in the previous example. And this is the symmetric powers of n symmetric powers. And here, if large n is equal 1, then this is Hilbert scheme points. And this is a resolution. If you put this stability parameter here. In some sense, somehow this adding n-dimensional vector space in this construction is very natural to me. And I think I will explain tomorrow the what we call Quivagate theory, then you will see more examples. Yeah, in general, we studied what happened to in semi-simple rank 1 case. And I think that if the Coulomb branch is a surface, this is always either type A or type D singularity, simple singularity. And the type D singularity appears if I consider SL2 instead of GL2. But we never get the type E singularities or other singularities. That is one of the